resolution. अब आखिरी लेयर की बात करें तो इसमें 10 न्यूरॉन्स होते हैं जो हर एक डिजिट को दर्शाते हैं। इन न्यूरॉन्स में जो एक्टिवेशंस
Neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between, called the hidden layers, which, for the time being, should just be a giant question mark for how on earth this process of Last video, I laid out the structure of a neural network. I'll give a quick recap here, just so that it's fresh in our minds, and then I have two main goals for this video. The first is to introduce the idea of gradient descent, which underlies not only how neural networks learn, but how a lot of other machine learning works as well. Then after that, we're going to dig in a little more to how this particular network performs, and what those hidden layers of neurons end up actually looking for. As a reminder, our goal here is the classic example of handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in the input layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked through last video. In total, given the somewhat arbitrary choice of two hidden layers here with 16 neurons each, the network has about 13,000 weights and biases that we can adjust. And it's these values that determine what exactly the network, actually does. Then what we mean when we say that this network classifies a given digit is that the brightest of those 10 neurons in the final layer corresponds.
Guys, I'm getting really tired and bored, so I'ma just do some exercise. थोड़ा सा freshen up हो जाता हूँ. Also, this hand is hurting pretty bad. Yeah, only 40 minutes in this live. But yeah, let me do some exercise. I'll only use my left hand. Okay, I'll be right back in 5 to 10 minutes.
to that digit. And remember, the motivation that we had in mind here for the layered structure was that maybe the second layer could pick up on the edges, and the third layer might pick up on patterns like loops and lines, and the last one could just piece together those patterns to recognize digits. So here, we learn how the network learns. What we want is an algorithm where you can show this network a whole bunch of training data, which comes in the form of a bunch of different images of handwritten digits, along with labels for what they're supposed to be, and it'll adjust those 13,000 weights and biases so as to improve its performance on the training data. Hopefully, this layered structure will mean that what it learns generalizes to images beyond that training data. And the way we test that is that after you train the network, you show it more labeled data that it's never seen before, and you see how accurately it classifies those new images. Fortunately for us, and what makes this such a common example to start with, is that the good people behind the MNIST database have put together a collection of tens of thousands of handwritten digit images, each one labeled with the numbers that they're supposed to be. And as provocative as it is to describe a machine as learning, once you actually see how it works, it feels a lot less like some crazy sci-fi premise, and a lot more like a calculus exercise. I mean, basically it comes down to finding the minimum of a certain function. Remember, conceptually, we're thinking of each neuron as being connected to all of the neurons in the previous layer, and the weights in the weighted sum defining its activation are kind of like the strengths of those connections, and the bias is some indication of whether that neuron tends to be active or inactive. And to start things off, we're just going to initialize all of those weights and biases totally randomly. Needless to say, this network is going to perform pretty horribly on a given training example, since it's just doing something random. For example, you feed in this image of a 3, and the output layer, it just looks like a mess. So what you do is you define this totally randomly. Needless to say, this network is going to perform pretty horribly on a given training example, since it's just doing something random. For example, you feed in this image of a 3, and the output layer, it just looks like a mess. So what you do is you define a cost function, a way of telling the computer, no, bad computer. That output should have activations which are 0 for most neurons, but 1 for this neuron. What you gave me is utter trash. To say that a little more mathematically, what you do is add up the squares of the differences between each of those trash output activations and the value that you want them to have. And this is what we'll call the cost of a single training example. Notice, this sum is small when the network confidently classifies the image correctly, but it's large when the network seems like it doesn't really know what it's doing. So then what you do is consider the average cost over all of the tens of thousands of training examples at your disposal. This average cost is our measure for how lousy the network is and how bad the computer should feel. And that's a complicated thing. Remember how the network itself was basically a function, one that takes in 784 numbers as inputs, the pixel values, and spits out 10 numbers as its output. And in a sense, it's parameterized by all these weights and biases. Well, the cost function is a layer of complexity on top of that, those 13,000 or so weights and biases, and it spits out a single number describing how bad those weights and biases are, and the way it's defined depends on the network's behavior over all the tens of thousands of pieces of training data. That's a lot to think about. But just telling the computer what a crappy job it's doing isn't very helpful. You want to tell it how to change those weights and biases so that it gets better. To make it easier, rather than struggling to imagine a function with 13,000 inputs, just imagine a simple function that has one number as an input and one number as an output. How do you find an input that minimizes the value of this function? Calculus students will know that you can sometimes figure out that minimum explicitly, but that's not always feasible for really complicated functions. Certainly not in the 13,000 input version of this situation for our crazy complicated neural network cost function. A more flexible tactic is to start at any old input and figure out which direction you should step to make that output lower. Specifically, if you can figure out the slope of the function where you are, then shift to the left if that slope is positive, and shift the input to the right if that slope is negative. If you do this repeatedly, at each point checking the new slope and taking the appropriate step, you're going to approach some local minimum of the function. And the image you might have in mind here is a ball rolling down a hill. And notice, even for this really simplified single input function, there are many possible valleys that you might land in, depending on which random input you start at. And there's no guarantee that the local minimum you land in is going to be the smallest of the cost function. That's going to carry over to our neural network case as well. And I also want you to notice how if you make your step sizes proportional to the slope, then when the slope is flattening out towards the minimum, your steps get smaller and smaller, and that kind of helps you from overshooting. Bumping up the complexity a bit, imagine instead a function with 2 inputs and 1 output. You might think of the input space as the xy plane, and the cost function as being graphed as a surface above it. Now instead of asking about the slope of the function, you have to ask which direction should you step in this input space so as to decrease the output of the function most quickly. In other words, what's the downhill direction? And again, it's helpful to think of a ball rolling down that hill. Those of you familiar with multivariable calculus will know that the gradient of a function gives you the direction of steepest ascent. Basically, which direction should you step to increase the function most quickly? Naturally enough, taking the negative of that gradient gives you the direction to step that decreases the function most quickly. And even more than that, the length of this gradient vector is actually an indication for just how steep that steepest slope is. Now, if you're unfamiliar with multivariable calculus and you want to learn more, check out some of the work that I did for Khan Academy on the topic. Honestly though, all that matters for you and me right now is that in principle there exists a way to compute this vector that tells you what the downhill direction is and how steep it is. You'll be okay if that's all you know and you're not rock solid on the details. Because if you can get that, the algorithm for minimizing the function is to compute this gradient direction, then take a small step downhill, and just repeat that over and over. It's the same basic idea for a function that has 13,000 inputs instead of 2 inputs. Imagine organizing all 13,000 weights and biases of our network. Imagine organizing all 13,000 weights and biases of our network into a giant column vector. The negative gradient of the cost function is just a vector. It's some direction inside this insanely huge input space that tells you which nudges to all of those numbers is going to cause the most rapid decrease to the cost function. And of course, with our specially designed cost function, changing the weights and biases to decrease it means making the output of the network on each piece of training data look less like a random array of 10 values and more like an actual decision that we want it to make. It's important to remember, this cost function involves an average over all of the training data, so if you minimize it, it means it's a better performance on all of those samples. The algorithm for computing this gradient efficiently, which is effectively the heart of how a neural network learns, is called backpropagation, and it's what I'm going to be talking about next video. There, I really want to take the time to walk through what exactly happens to each weight and each bias for a given piece of training data, trying to give an intuitive feel for what's happening beyond the pile of relevant calculus and formulas. Right here, right now, the main thing I want you to know, independent of implementation details, is that what we mean when we talk about a network learning is that it's just minimizing a cost function. And notice, one consequence of that is that it's important for this cost function to have a nice, smooth output, so that we can find a local minimum by taking little steps downhill. This is why, by the way, artificial neurons have continuously ranging activations, rather than simply being active and find a local minimum by taking little steps downhill. This is why, by the way, artificial neurons have continuously ranging activations, rather than simply being active or inactive in a binary way, the way that biological neurons are. This process of binary way, the way that biological neurons are, rather than simply being active or inactive in a binary way, the way that biological neurons are. This process of repeatedly nudging an input of a function by some multiple of the negative gradient is called gradient descent. It's a way to converge towards some local minimum of a cost function, basically a valley in this graph. I'm still showing the picture of a function with two inputs, of course, because nudges in a 13,000 dimensional input space are a little hard to wrap your mind around, but there is actually a nice non-spatial way to think about this. Each component of the int tells us two things. The sign, of course, tells us whether the corresponding component of the input vector should be nudged up or down. But importantly, the relative magnitude of things. The sign, of course, tells us whether the corresponding component of the input vector should be nudged up or down. But importantly, the relative magnitude vector should be nudged up or down. But importantly, the relative magnitudes of all these components kind of tells you which changes matter more. You see, in our network, an adjustment to one of the weights might have a much greater impact on the cost function than the adjustment to some other weight. Some of these connections just matter more for our training data. So a way that you can think about this gradient vector of our adjustment to some other weight. Some of these connections just matter more for our training data. So a way that you can think about this gradient vector of our mind-warpingly massive cost function is that it encodes the relative importance of each weight and bias. That is, which of these changes is going to carry the most bang for your buck. This really is just another way of thinking about direction. To take a simpler example, if you have some function with two variables as an input, and you compute that its gradient at some particular point comes out as 3, 1, then on the one hand, you can interpret that as saying that when you're standing at that input, moving along this direction increases the function most quickly. That when you graph the function above the plane of input points, that vector is what's giving you the straight uphill direction. But another way to read that is to say that changes to this first variable have 3 times the importance as changes to the second. That, at least in the neighborhood of the relevant input, nudging the x value carries a lot more bang for your buck. Alright, let's zoom out and sum up where we are so far. The network itself is this function with 784 inputs and 10 outputs, defined in terms of all of these weighted sums. The cost function is a layer of complexity on top of that. It takes the 13,000 weights and biases as inputs and spits out a single measure of lousiness based on the training examples. And the gradient of the cost function is one more layer of complexity still. It tells us what nudges to all of these weights and biases cause the fastest change to the value of the cost function, which you might interpret as saying which changes to which weights matter the most. So, when you initialize the network with random weights and biases and adjust them many times based on this gradient descent process, how well does it actually perform on images that it's never seen before? Well, the one that I've described here, with the 2 hidden layers of 16 neurons each, chosen mostly for aesthetic reasons, well, it's not bad. It classifies about 96% of the new images that it sees correctly. And honestly, if you look at some of the examples that it messes up on, you kind of feel compelled to cut it a little slack. Never seen before, given that we never specifically told it what pattern. Remember how last video we looked at how the weights of the connections from all of the neurons in the first layer to a given neuron in the second layer can be visualized as a given pixel pattern that second layer neuron is picking up on? Well, when we actually do that for the weights associated with these transitions from the first layer to the next, instead of picking up on isolated little edges here and there, they look, well, almost random, just with some very loose patterns in the middle there. It would seem that in the unfathomably large 13,000 dimensional space of possible weights and biases, our network found itself a happy little local minimum that, despite successfully classifying most images, doesn't exactly pick up on the patterns that we might have hoped for. And to really drive this point home, watch what happens when you input a random image. If the system was smart, you might expect it to either feel uncertain, maybe not really activating any of those 10 output neurons or activating them all evenly. But instead, it confidently gives you some nonsense answer, as if it feels as sure that this random noise is a 5 as it does that an actual image of a 5 is a 5. Phrased differently, 5 as it does that an actual image of a 5 is a 5. Phrased differently, even if this network can recognize digits pretty well, it has no idea how to draw them. A lot of this is because it's such a tightly constrained training setup. I mean, put yourself in the network's shoes here. From its point of view, the entire universe consists of nothing but clearly defined, unmoving digits centered in a tiny grid. And its cost function just never gave it any incentive to be anything but utterly confident in its decisions. So with this as the image of what those second-layer neurons are really doing, you might wonder why I would introduce this network with the motivation of picking up on edges and patterns. I mean, that's just not at all what it ends up doing. Well, this is not meant to be our end goal, but instead a starting point. Frankly, this is old technology, the kind researched in the 80s and 90s. And you do need to understand it before you can understand more detailed modern variants, and it clearly is capable of solving some interesting problems. But the more you dig into what those hidden layers are really doing, the less intelligent it seems. In the 80s and 90s. And you do need to understand it before you can understand more detailed modern variants, and it clearly is capable of solving some interesting problems. But the more you dig into what those hidden layers are really doing, the less intelligent it seems. Shifting the focus for a moment from how networks learn to how you learn, engage actively with the material here somehow. One pretty simple thing that I want you to do is just pause right now and think deeply for a moment about what changes you might make to this system and how it perceives images if you wanted it to better pick up on things like edges and patterns. But better than that, to actually engage with the material, I highly recommend the book by Michael Nielsen on deep learning and neural networks. In it, you can find the code and the data to download and play with for this exact example, and the book will walk you through step by step what that code is doing. What's awesome is that this book is free and publicly available, so if you do get something out of it, consider joining me in making a donation towards Nielsen's efforts. I've also linked a couple other resources that I like a lot in the description, including the phenomenal and beautiful blog posts by Chris Olah and the articles in Distill. To close things off here for the last few minutes, I want to jump back into a snippet of the interview that I had with Leisha Lee. You might remember her from the last video. She did her PhD work in deep learning. And in this little snippet, she talks about two recent papers that really dig into how some of the more modern image recognition networks are actually learning. Just to set up where we were in the conversation, the first paper took one of these particularly deep neural networks that's really good at image recognition, and instead of training it on a properly labeled dataset, it shuffled all of the labels around before training. Obviously, the testing accuracy here was going to be no better than random.
To light another paper from actually a couple of years ago, which has a lot more simplifications about the network layers, but one of the results was saying how
Hello. Okay, so I have completed this second lecture. Okay, and I will just write down the stuff that I remember. Okay. ठीक है 25 whatever, ठीक है. So first of all, भाई मैं उसका नाम कैसे भूल गया, टॉपिक का नाम कैसे भूल गया. ग्रेडियंट डिसेंट. हाँ, gradient descent. This is basically the negative of del C. ठीक है. C del C negative of del C मतलब जो इनपुट फंक्शन है उसका जब हम 1 डिग्री डेरिवेटिव लेंगे, ठीक है, तो जो उसका स्लोप आएगा, जो उसका स्टीप आएगा उसका नेगेटिव में, क्योंकि अगर पॉजिटिव स्लोप है, एंड पॉजिटिव स्लोप कैसे आएगा, इफ दिस एंड पॉजिटिव स्लोप एज इन दिस, ठीक है, दिस पार्ट. तो अगर वो जो दो आउटपुट के लिए अगर ये पॉजिटिव स्लोप आ रहा है, ठीक है, तो हमको इसको मिनिमाइज़ करना है, इसको हम लोकल मिनिमा पे पहुंचना है, ठीक है. तो लोकल मिनिमा पे जब पहुंच पाएंगे, जब इसको अपन नीचे ला रहे होंगे जो आउटपुट आ रहा है, ठीक है, वो कैसे आएगा, क्योंकि इसका पॉजिटिव स्लोप है, दिस इज़ अ पॉजिटिव स्लोप, ठीक है, ये पॉजिटिव स्लोप है. तो हमको नीचे लेके आना है. नीचे कैसे लेके आएंगे, अगर हम उसको नीचे लेके आ जाएंगे ऐसे नेगेटिव स्लोप अगर कर देंगे उसका, नेगेटिव स्लोप मतलब नेगेटिव ऑफ डेल्टा सी. डेल्टा सी इज़ बेसिकली द स्लोप एंड नेगेटिव ले लेंगे उसका टू ब्रिंग डाउन द वैल्यू ऑफ द आउटपुट. एंड बेसिकली हमारा गोल होता है कि हमको लोकल मिनिमा पे कॉन्सेंट्रेट करते रहना है सारी वैल्यूज़ को, ताकि जो आउटपुट आए उसका कैसे बताऊँ मैं, जो कॉस्ट फंक्शन है वो कॉस्ट फंक्शन मिनिमम आए, मतलब मिनिमम कॉस्ट फंक्शन पे हम पहुंच पाएँ. तो हमारा ये गोल होता है. एंड इस प्रोसेस को जो नज कर रहे हैं हम इनपुट्स को, नजिंग लाइक द प्रोसेस ऑफ नजिंग द इनपुट्स इज कॉल्ड ग्रेडियंट डिसेंट. या एंड और क्या देखा था इसमें मैंने, एक बार मैं देख लेता हूँ वीडियो को स्क्रॉल करके. हाउ न्यूरल नेटवर्क्स लर्न. हाँ ठीक है, हाउ न्यूरल नेटवर्क्स लर्न में आएगा कि उनको हम लेबल सेट ऑफ डेटा देते हैं. जैसे हैंड राइटिंग डिटेक्शन वाला है, अगर जैसे उसमें अगर हैंड जो नंबर्स है सारे, तो 0 से लेके 9 तक, तो जो इतना बड़ा सेट ऑफ डेटा रहेगा उसमें हम लेबल करके रहेंगे. जैसे अगर हम एक हैंड रिटन 0 का डेटा उसमें डाला है तो उसके साथ लेबल करेंगे कि दिस इज़ 0, ठीक है. ऐसे करके मल्टीपल डेटा हमारा उसमें रहेगा, थाउजेंड्स ऑफ, या अच्छे डेटा सेट्स तो बहुत बड़े बड़े डेटा रखते हैं, लाइक बिग नंबर ऑफ डेटास, ठीक है. एंड वो लेबल डेटा रहेगा, तो उस पर जो ये है एक जो अपना एल्गो है, मशीन है जो, वो रैंडम व्हाट वाज द वर्ड फॉर इट, वेट, बायस, आई गेस बायस था. हाँ, तो रैंडम बायसेस पे लेके रैंडम वेट्स या तो रैंडम बायस, अब दोनों में से एक है. एंड आई विल गेट टू इट, लाइक मे बी आई विल गेट इनटू दिस फ्लो कुछ दिनों में. अभी तो मेरे को थोड़ा फॉरेन कॉन्सेप्ट लगता है, बट हाँ, तो रैंडम वैल्यूज़ ऑफ बायस और रैंडम वैल्यूज़ ऑफ वेट्स को इस मशीन के जो मल्टीपल लेयर्स है ना, उनसे गो थ्रू करेगा, ठीक है. फर्स्ट लेयर पे पहुँचेगा, सेकंड लेयर पे पहुँचेगा, ऐसे ऐसे करके, एंड देन आउटपुट लेयर तक पहुँचेगा, ठीक है. एंड 0 से लेके 1 में जो आउटपुट के जो नोड्स रहेंगे उनमें क्या वैल्यूज़ रह सकती है. जैसे अगर ये नोड है, एक ये नोड है, एक ये नोड है, तो इनमें जो वैल्यूज़ रहेगी वो 0 to 1 के बीच में कुछ एक वैल्यू रहेगा, ठीक है. विच मीन्स कि 0, अगर जो आउटपुट आ रहा है वो 0 तक है, तो देन इट इज़ लेस प्रोबेबल. 1 है तो देन इट इज़ मोस्ट प्रोबेबल। जैसे अगर ये 0 है, ये 1 है, ये 2 है, इसका यहाँ पे वैल्यू हमारा आ रहा है 0.9, यहाँ पे आ रहा है 0.5, यहाँ पे आ रहा है 0.4, तो 1 होने लाइक जो अपना इनपुट है दैट इज़ मोस्ट प्रोबेबल टू बी 1। ठीक है, तो दिस इज़ हाउ द नोड्स वर्क, न्यूरल नोड्स वर्क। एंड वे वाज आई, लाइक कहाँ से स्टार्ट किया था ऐसा मैंने? वेट, लेट मी चेक इफ माई माइक इज ऑन, हाउ डू गेट इट्स ऑन। मैं ट्रेन ऑफ थॉट छूट गई मेरे से। हाँ, हाउ मशीन्स लर्न। तो मल्टीपल डेटास का ऐसा ऐसा रैंडम बायस एंड रैंडम वेट्स को इन सारे लेयर से गो थ्रू कर करके जो भी वैल्यूज़ आ रही होंगी वो, जैसे ये जो मल्टीपल नोड्स पे जो उनकी वैल्यूज़ 0 से लेकर 1 तक कुछ आएगा, ठीक है। एंड उन वैल्यूज़ में से हम माइनस कर रहे होंगे जो, जैसे हमको पता है, अगर जैसे मानो कि अगर मैंने इनपुट डाला 1 है, ठीक है, 1 लिखा हुआ है, एंड जो भी इस पर वैल्यूज़ आई है, जैसे इस पर मानो इस पर अगर 0.7 आई है, इस पर 0.6 आई है, इस पर 0.4 आई है, तो इन सब को हम, जैसे 0.9 आई है किसी पे, तो 0.9 का स्क्वायर माइनस 1 का स्क्वायर, नो वेट, 0.9 माइनस 1 का होल स्क्वायर, ऐसा कुछ तो फंक्शन था। एंड इसको हम निकाल लेंगे। एंड जिस भी केस में ये जो हम ऑपरेशन कर रहे हैं, उसके बाद जिस भी नोड पे सबसे लीस्ट वैल्यू आ रही होगी, तो हम बोल देंगे कि ठीक है, दैट इज़ द मोस्ट प्रोबेबल नोड, मतलब वो आउटपुट हमारा मोस्ट प्रोबेबल है। एंड जो नेगेटिव, जो मतलब ये जो हम सबसे कम लाना है, वो जब भी आएगा जब ये सबसे 1 के नज़दीक होगा, ठीक है। एंड ये जब होगा जब कॉस्ट फंक्शन हमारा मिनिमम होएगा। तो लाइक ऑल ऑफ दिस रैंडम शिट जस्ट टू bring this cost function to its low, to the lowest value, and so that we get, इस प्रोसेस के बाद हमको 0.0 लाइक 0.1 एंड 0 से लेकर 0.1 के बीच में, लाइक 0 को 10 करते हुए जो भी वैल्यू मिल रही होगी, ठीक है। सो या दिस प्रोसेस इज कॉल्ड एज ग्रेडियंट डिसेंट। बेसिकली हमको लोकल मिनिमा से पहुंचना है, ठीक है। एंड वो हम रैंडम पॉइंट्स पे चालू करते हैं। एंड जैसे मानो अगर नहीं, ये तो गलत हो गया, अगर यहाँ से चालू किया है तो ये यहाँ पे जाएगा, ठीक है, ये चालू किया तो यहाँ पे जाएगा, तो ये एक पॉइंट, ये एक पॉइंट, तो यहाँ पे 2 लोकल मिनिमास हो रहे हैं, ठीक है। एंड ये वाला इसमें, जैसे इस केस में ये वाला ग्लोबल मिनिमा भी है क्योंकि ये नीचे है एंड ये वाला ऊपर है। तो ग्लोबल मिनिमा तक पहुँचना इज़ वेरी लेथार्जिक एंड वेरी टायर्ड, लाइक वेरी टायर्डसम प्रोसेस। एंड इसलिए हम रैंडम पॉइंट्स से स्टार्ट करते हैं एंड वहाँ से देखते हैं लोकल मिनिमास पे पहुँचने का ट्राई करते हैं। ओके, सो दिस वाज द सेकंड लेक्चर एंड ये सब इसमें कवर हुआ है। अभी आई एम थिंकिंग ऑफ गोइंग टू द थर्ड लेक्चर, बिकॉज टेक्निकली मैंने सेकंड लेक्चर पहले भी देखा था, बट मुझे उस समय समझ नहीं आया था क्योंकि मेरा दिमाग थोड़ा काम नहीं कर रहा था उस समय। अब इसमें बैक प्रोपोगेशन एंड मेरे को जितना पता चला था कि बैक प्रोपोगेशन इज़ रियली इंपॉर्टेंट, बिकॉज यहाँ पे हमको पता चलता है हाउ द इंटरनल लेयर्स एक्चुअली वर्क, जो अभी तक तो ऐसा हमको डीप डाइव नहीं किया था उसमें, बेसिकली इग्नोर ही कर दिया था कि कुछ हो रहा है, कुछ हो रहा है, बट यहाँ पे एक्चुअली में क्या हो रहा है वो देखना आपको मिलेगा। तो आई एम गोना स्टार्ट दिस एंड आई एम प्लानिंग ऑन स्टडीइंग टिल 1:30 या 2 एट मैक्स, ठीक है। तो उसके लिए 2 घंटे मेरे पास बचे हुए हैं, तो लेट्स सी। आई एम गोना स्टार्ट दिस वीडियो एंड आई डू द सेम प्रोसेस। वीडियो ख़त्म होने के बाद आई जस्ट स्क्रिबल कि मेरे को क्या क्या याद आया इससे, ताकि मेरे को थोड़ा दिमाग में जाए भी, रिपीट करूँगा, सुनाई देगा। ओके, सो आई एम गोना स्टार्ट द थर्ड लेक्चर, स्टार्ट विद द थर्ड लेक्चर। इंग्लिश भी सही करनी है मेरे को। न्यूरल नेटवर्क लेक्चर 2 तो हो गया मेरा, सो आई एम गोना इरेज दिस पार्ट एंड अब यही एक बचा है, ठीक है। ओके, सो आई एम गोना म्यूट माई सेल्फ एंड गोना स्टार्ट द थर्ड लेक्चर।
Here, we tackle back propagation, the core algorithm behind how neural networks learn. After a quick recap for where we are, the first thing I'll do is an intuitive walkthrough for what the algorithm is actually doing, without any reference to the formulas. Then, for those of you who do want to dive into the math, the next video goes into the calculus underlying all this. If you watched the last two videos, or if you're just jumping in with the appropriate background, you know what a neural network is, and how it feeds forward information. Here we're doing the classic example of recognizing handwritten digits, whose pixel values get fed into the first layer of the network with 784 neurons, and I've been showing a network with two hidden layers having just 16 neurons each, and an output layer of 10 neurons, indicating which digit the network is choosing as its answer. I'm also expecting you to understand gradient descent, as described in the last video, and how what we mean by learning is that we want to find which weights and biases minimize a certain cost function. As a quick reminder, for the cost of a single training example, what you do is take the output that the network gives, along with the output that you wanted it to give, and you just add up the squares of the differences between each component. Doing this for all of your tens of thousands of training examples and averaging the results, this gives you the total cost of the network. And as if that's not enough to think about, as described in the last video, the thing that we're looking for is the negative gradient of this cost function, which tells you how you need to change all of the weights and biases, all these connections, so as to most efficiently decrease the cost. Backpropagation, the topic of this video, is an algorithm for computing that crazy complicated gradient. And the one idea from the last video that I really want you to hold firmly in your mind right now is that because thinking of the gradient vector as a direction in 13,000 dimensions is, to put it lightly, beyond the scope of our imaginations, there's another way you can think about it. The magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. For example, let's say you go through the process I'm about to describe and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2. while the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost, and that change is 32 times greater than what the same wiggle to that second weight would give. While the component go through the process I'm about to describe, and you compute the negative component associated with the weight on this edge here comes out to be 3.2, while the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost, and that change is 32 times greater than what the same wiggle to that second weight would give. Personally, when I was first learning about backpropagation, I think the most confusing aspect was just the notation and the index chasing of it all. But once you unwrap what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm going to start things off here with a complete disregard for the notation, and just step through those effects that each training example is having on the weights and biases. Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations, we only have influence on the weights and biases, but it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify activations, we only have influence on the weights and biases, but it is helpful to keep track of which adjustments yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations, we only have influence on the weights and biases, but it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up. We want it to track your work is a certain cost per spacing of it all. But once you unwrap what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm going to start things off here with a complete disregard for the notation, and just step through those effects that each training example is having on the weights and biases. Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations, we only have influence on the weights and biases, but it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigma value. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down, we care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a 2 get more strongly linked to those firing when thinking about a 2. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together wire together idea comes with a couple meaningful asterisks. But, taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. Connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, this is only with those biases. But just weight change digit 2. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, the digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to this second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listen to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through this same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes. This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video, or at least something proportional to it. I say loosely speaking referenced in the last video, or at least something proportional to it. I say loosely speaking only because I have yet to get quantitatively precise about those nudges. But if you understood every change that I just referenced, why some are proportionally bigger than others, and how they all need to be added together, you understand the mechanics for what backpropagation is actually doing. By the way, in practice, it takes computers an extremely long time to add up the influence of every single training example, every single gradient descent step. So here's what's commonly done instead. You randomly shuffle your training data and then divide it into a whole bunch of mini batches, let's say each one having 100 training examples. Then you compute a step according to the mini batch. It's not going to be the actual gradient of the cost function, which depends on all of the training data, not this tiny subset. So it's not the most efficient step downhill. But each mini batch does give you a pretty good approximation, and more importantly, it gives you a significant computational speedup. If you were to plot the trajectory of your network under the relevant cost surface, it would be a little more like a drunk man stumbling aimlessly down a hill, but taking quick steps, rather than a carefully calculating man determining the exact downhill direction of each step before taking a very slow and careful step in that direction. This technique is referred to as stochastic gradient descent. There's kind of a lot going on here, so let's just sum it up for ourselves, shall we? Backpropagation is the algorithm for determining how a single training example would like to nudge the weights and biases, not just in terms of whether they should go up or down, but in terms of what relative proportions to those changes cause the most rapid decrease to the cost. A true gradient descent step would involve doing this for all your tens and thousands of training examples and averaging the desired changes that you get. But that's computationally slow, so instead you randomly subdivide the data into these mini batches and compute each step with respect to a mini batch. Repeatedly going through all of the mini batches and making these adjustments, you will converge towards a local minimum of the cost function, which is to say your network is going to end up doing a really good job on the training examples. So with all of that said, every line of code that would go into implementing backprop actually corresponds with something that you have now seen, at least in informal terms. But sometimes knowing what the math does is only half the battle, and just representing the damn thing is where it gets all muddled and confusing. So, for those of you who do want to go deeper, the next video goes through the same ideas that were just presented here, but in terms of the underlying calculus, which should hopefully make it a little more familiar as you see the topic in other resources. Before that, one thing worth emphasizing is that for this algorithm to work, and this goes for all sorts of machine learning beyond just neural networks, you need a lot of training data. In our case, one thing that makes handwritten digits such a nice example is that there exists the MNIST database with so many examples that have been labeled by humans. So a common challenge that those of you working in machine learning will be familiar with is just getting the labeled training data that you actually need, whether that's having people label tens of thousands of images or whatever other data type you might be dealing with.
Okay, so I'm gonna try and in a very lame language, I'm gonna try to just recap कि मैंने क्या क्या पढ़ा है इसमें, but in a very lame language. Also यार इसका ये इतनी गंदी क्वालिटी क्यों आती है इसकी यार, कुछ तो सीन है इसमें भी, गंदी आ रही है। खैर जो भी है, ठीक है चलो। हाँ, तो इसमें अब हम समझेंगे कि बैक प्रोपगेशन कैसे होता है। बैक प्रोपगेशन क्या होता है ये तो अपन ने देख लिया था, वेट नो, हमने देखा नहीं था। बट बैक प्रोपगेशन इज एक्चुअली, बैक प्रोपगेशन क्या होता है? बैक प्रोपगेशन इज द प्रोसेस वेयर वी एक्चुअली डू द ग्रेडियंट डिसेंट वाला थिंग, नेगेटिव डेल सी वाला जो प्रोसेस था, वो जो हम एक्चुअली कर रहे होते हैं, कब कर पाते हैं? ड्यूरिंग बैक प्रोपगेशन। बैक प्रोपगेशन इज बेसिकली जो जैसे एक ये लेयर है, ठीक है, एक ये लेयर है, एक ये लेयर है एंड ये आउटपुट लेयर है, ठीक है। अब इसमें क्या होता है कि आउटपुट लेयर में जैसे कि 1 2 4 ऐसे कर करके 9 तक होएगा, ठीक है, 0 से लेके 9 तक होगा, 0 से लेके 9 तक। तो इसमें हमने इसमें एक एग्जांपल लिया था, ठीक है। एग्जांपल में 2 लिखा हुआ था, 2 का इनपुट था एंड लेबल क्योंकि मैंने बताया था ना कि उसमें लेबल भी रहता है, तो लेबल करके लिखा हुआ था कि दिस इज़ अ 2, ठीक है। एंड उसमें क्योंकि जो स्टार्टिंग में वैल्यूज़ आ रही होती है दे आर वेरी रैंडम एंड मशीन इज़ बेसिकली लर्निंग, तो वो बहुत ही रैंडम से वैल्यूज़ होती हैं। तो इसमें एग्जांपल लिया था कि जो 2 है, जैसे कि 0 है, ये 1 है, ये 2 है, ये 3 है, ऐसे कर करके था 9 तक। एंड इसकी वैल्यू जैसे मानो अगर 0 की वैल्यू 0.2 आ रही है, 0 की वैल्यू 0.2, 1 की वैल्यू 0.8, 3 की वैल्यू 0.8, ठीक है, ऐसा कर करके होएगा। तो हमारा गोल है कि जो ये है, बिकॉज इस एग्जांपल में हमने 2 लिया है, तो हमको इस नोड की वैल्यू को मैक्सिमाइज़ करना है। मैक्सिमाइज़ करना है मतलब नियर टू 1 लेके आना है। बट व्हेन विल दिस एक्चुअली हैपन? दिस विल हैपन व्हेन इसके जो प्रीवियस लेयर है, इसके जो सारे लिंक्स की वजह से, एंड ये 13,000 कुछ तो रहता है, आई गेस 13,002 रहती है ये सारी, क्योंकि इस नोड पे ये सब पे कनेक्टेड है, ठीक है। ये मैं सिर्फ इस केस की बात कर रहा हूँ। एंड इस केस में क्या रहेगा, अब मैं ब्लू से यूज़ करूँगा, ठीक है, ब्लू यूज़ करूँगा टू शो कि जिसकी ज़्यादा है एंड ब्लैक जिसकी कम है, पता नहीं, ठीक है। ब्लू 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 एंड ब्लैक एंड ब्लैक, ठीक है। ब्लैक मीन्स कि ये जो है लेस एक्टिवेटेड है, ब्लू मीन्स दिस इज़ हाईली एक्टिवेटेड। हमारा गोल है कि जो 0.2 तक हमको पहुंचना है इन अ वे कि जो वेट्स, ठीक है, जो इनके सारे वेट्स की एक वैल्यू होती है, ठीक है। एंड हमारा गोल है कि जो 0.2 है इसको हमको 1 के पास लेके आना है। अब ये 3 वेज में हो सकता है। एक होता है अगर हम वेट्स को मैनिपुलेट करें, एक होता है अगर हम बायस को मैनिपुलेट करें, एक होता है अगर एक्टिवेशन एनर्जी को मैनिपुलेट करें, ठीक है। बायस एक सिंगुलर क्वांटिटी रहेगा, ये प्लस में रहेगा, A नॉट W नॉट ऐसे कर करके, ठीक, इन सब में हम बायस सेट कर रहे होंगे एंड उसके ऊपर हम सिग्नॉइड फंक्शन डाल देंगे, ठीक है। तो ये मैथमेटिकल फंक्शन वो लाइक ये सारी कैलकुलेशंस होके यहाँ पे जो वैल्यू है ये पूरी इफेक्ट हो रही है। अब हमारा गोल है कि 0.2 को हमको 1 के पास लेके आना है। ये जब हो पाएगा जब हम या तो A को नच करें, या तो W को, या तो बेस को, बायस को नच करें, या वेट्स को नच करें। ठीक है। वेट्स एज इन कि इसका एक पर्टिकुलर वेट होता है, इसका एक पर्टिकुलर वेट है, इसका एक पर्टिकुलर वेट है, इसका एक पर्टिकुलर वेट है, ठीक है। हमारा गोल ये है लॉजिस्टिकली स्पीकिंग कि जिन नोड्स पे जो हमारा हाईली एक्टिवेटेड नोड्स हैं उनको पहले हमको जो उनके वेट्स हैं, ठीक है, उनके वेट्स को ऊपर लेके आना है, उनके वेट्स को ऊपर लेके आना है, ठीक है, ताकि जो ये एंडिंग में जो ये अब वेट बढ़ेगा तो मतलब सारे वेट्स को अगर एक वेट की बात करूँ तो इसको हम बढ़ाएंगे तो इसकी वैल्यू थोड़ी सी बढ़ेगी जो ये ओवरऑल है, एंड यही ओवरऑल ये जो निकल रहा है हमारा 0.2 ये है, ठीक है। तो हमारा गोल है कि 0.2 को बढ़ाना है, तो 0.2 को बढ़ाने के लिए हमको इसका वेट बनाना पड़ेगा। वेट उनके बढ़ाने पे पहले फोकस ज़्यादा करेंगे जिनकी ज़्यादा एक्टिवेटेड है, लाइक जो एक्टिवेटेड ज़्यादा है, एक्टिवेशन जिनकी ज़्यादा है, ठीक है। एंड इस जो ब्लैक है इन सब की हमको नीचे लगाना होगा वेट, ठीक है, समझे आप। इसका वाला नीचे लाना होगा, ये इसको ऊपर लेके आना होगा, इसको ऊपर लेके आना होगा, तो ये प्रोसेस है, ठीक है। अब ये बात हो गई कि हम वेट्स का क्या करेंगे, एक्टिवेशन का कैसे करेंगे हम। एक्टिवेशन का हमारा ये गोल रहेगा कि ये जो ब्लैक वाले हैं इनकी एक्टिवेशन और कम करें, एंड ये जो पॉजिटिव वैल्यूज़ पॉजिटिव इन्फ्लुएंस जिनका है ज़्यादा उनकी हमको एक्टिवेशन और ज़्यादा करनी है। बट दिस प्रोसेस वुड एक्चुअली इंक्लूड इसका जो प्रीवियस लेयर है उसको, ठीक है, ये वाली जो लेयर है इसको, एंड क्योंकि इसकी वजह से ही जो ये इनकी एक्टिवेशंस हैं वो सारी इन्फ्लुएंस हो रही हैं। अब इसमें क्या होगा, मतलब रिकर्सिव अप्रोच यूज़ करेंगे हम कि ये जो है ब्लू है ना, इसको हमको और ब्लू करना है, मतलब इसको और एक्टिवेटेड करना है। वो कैसे करेंगे कि इसके जो सारे लिंक्स होंगे, मतलब इसके जो ये सारे ऐसे करके बहुत सारे लिंक्स होंगे ना, उनको हमको यहाँ पे देखना पड़ेगा, ठीक है। उनमें जो वीक स्पॉट्स रहेंगे उनको और नीचे लेके आना होगा, उनमें जो ब्राइट स्पॉट्स रहेंगे, ब्राइट नोट्स रहेंगे, उनको और ऊपर लेके आना पड़ेगा। बेसिकली सेम अप्रोच अगेन, लाइक रिकर्सिव अप्रोच कर रहे होंगे। तो ऐसा करके हमको करना है, ठीक है। यहाँ ऐसे करके चेंजेस करके हमको बेसिकली इसको नियर टू 1 लेके आना है, एंड इन सबको कम भी करना है, ठीक है। बट पहला गोल रहेगा कि जो 0.8 है इसको नीचे लाओ, एंड 0.2 इसको ऊपर लेके आओ। अब जैसे अगर 8 है तो 2 और 8 में तो बिल्कुल अंतर है ना। अगर जो 8 डिटेक्ट कर रहा है, 8 अगर मानो कि 0.2 डिटेक्ट कर रहा है तो उसको नीचे लाना इज़ लेस ऑफ अ प्रायोरिटी टू अस, लेसर देन दिस पार्ट जो हमको इसको ऊपर लेके आना है एंड इनको नीचे लेके आना है, ताकि सिस्टम एक लॉजिकली आउटपुट जनरेट कर पा रहा हो, ठीक है। और हाँ, ये तो बात हुई कि सिर्फ इस नोड की, बट हमको एक्चुअली क्या करना है, ये मतलब ये बात हुई सिर्फ 2 की, बट हमारे पास 1 3 5 4 5 9 मतलब 1 से लेके 9 तक और भी बहुत सारे इनपुट्स हैं। तो ये प्रोसेस हमको उनके लिए भी करनी पड़ रही होगी, क्योंकि अगर ये हम सिर्फ 2 पे ट्रेन कर देंगे तो फिर जो मशीन है वो सिर्फ ये 2 लाइक वो बस 2 के लिए ट्रेन हो पा रही होगी कि वो सारी इमेजेस को 2 डिटेक्ट कर रही होगी, जो कि नहीं करना है। तो ये जो प्रोसेस करी वो बाकी करना पड़ेगा इनके लिए भी, एंड जितना बड़ा डेटा सेट रहेगा उतना एक्यूरेसी हमारी ज़्यादा आ रही होगी। तो दिस वाज द प्रोसेस जहाँ पे हमको बैक प्रोपगेशन यूज़ कर रहे हैं, एंड पीछे जा के हमको पीछे वाले मतलब समझ रहे हो, ऐसे करके हम जो ये यहाँ पे जो फर्स्ट लेयर होगी इसकी, क्योंकि दिस इज़ द इनपुट पार्ट, ठीक है, ये जो फर्स्ट लेयर होगी यहाँ तक हमको पहुँचना है, इसको चेंज करना है, इसको चेंज करना है, इसको चेंज करना है, ऐसे करके आउटपुट तक पहुँच जाना है। इस प्रोसेस को कहते हैं बैक प्रोपगेशन, एंड इसका ये इंट्यूशन था कि कैसे काम हो रहा होता है। ये जो हमने एग्जांपल ये 2 के लिए लिया है, इसको हम और बाकी सबके साथ भी ट्रेन करेंगे, एंड बहुत ही ज़्यादा बड़ी प्रोसेस होगी, क्योंकि 13,000 वेट्स को हम मैनिपुलेट कर रहे होंगे। उनके पहले वाली लेयर्स में जाएंगे वो मैनिपुलेट करेंगे, उनके पहले वाली लेयर्स में जाएंगे वो मैनिपुलेट करेंगे। तो दिस इज़ अ वेरी बिग प्रोसेस, एंड yeah, this was the idea of propagation, the intuition behind it, and in the next lecture I will get to know the calculus part, like जो notations हैं उनको समझ में कैसे करें, समझें कैसे the code process, कोड में जो यूज़ हो रहा है कोड कैसे समझें, ये तो intuition था। बट हाँ, मतलब आई एम रियली हैप्पी कि मैं इतना समझ पा रहा हूँ, like I'm actually able to grasp the concept, And yeah, I'm thinking of hopping on to the next lecture because I'm really amused by this concept. मेरे को एक्चुअली समझ में आ भी रहा है, तो सोच रहा हूँ कि अब नेक्स्ट लेक्चर भी देख ही लेता हूँ इसका. गेट प्रेप का मैं 1:30 के बाद थोड़ा देखता हूँ, या 1 के बाद. अभी तो आधा घंटा बचा है. ओके, सो I'm gonna mute my mic again and I'm gonna hop on to the next lecture.
The hard assumption here is that you've watched part 3, giving an intuitive walkthrough of the backpropagation algorithm. Assumption here is that you've watched part 3, giving an intuitive walkthrough of the backpropagation algorithm. Here, we get a little bit more formal and dive into the relevant calculus. It's normal for this to be at least a little confusing, so the mantra to regularly pause and ponder certainly applies as much here as anywhere else. Our main goal is to show how people in machine learning commonly think about the chain rule from calculus in the context of networks, which has kind of a different feel from how most introductory calculus courses approach the subject. For those of you uncomfortable with the relevant calculus, I do have a whole series on the topic. Let's just start off with an extremely simple network, one where each layer has a single neuron in it. So this particular network is determined by 3 weights and 3 biases, and our goal is to understand how sensitive the cost function is to these variables. That way we know which adjustments to those terms is going to cause the most efficient decrease to the cost function. And we're just going to focus on the connection between the last 2 neurons. Let's label the activation of that last neuron with a superscript L indicating which layer it's in. So the activation of the previous neuron is AL-1. These are not exponents, they're just a way of indexing what we're talking about, since I want to save subscripts for different indices later on. Now let's say that the value we want this last activation to be for a given training example is y. For example, y might be 0 or 1. So the cost of this simple network for a single training example is AL minus y squared. We'll denote the cost of that one training example as C0. As a reminder, this last activation is determined by a weight, which I'm going to call WL, is AL minus y. Let's say that, which has kind of a different feel from how most introductory calculus courses approach the subject. For those of you uncomfortable with the relevant calculus, I do have a whole series on the topic. Let's just start off with an extremely simple network, one where each layer has a single neuron in it. So this particular network is determined by 3 weights and 3 biases, and our goal is to understand how sensitive the cost function is to these variables. That way we know which adjustments to those terms is going to cause the most efficient decrease to the cost function. And a really simple network, one where each layer has a single neuron in it. So this particular network is determined by 3 weights and 3 biases, and our goal is to understand how sensitive the cost function is to these variables. That way we know which adjustments to those terms is going to cause the most efficient decrease to the cost function. And we're just going to focus on the connection between the last 2 neurons. Let's label the activation of that last neuron with a superscript L, indicating which layer it's in. So the activation of the previous neuron is AL-1. These are not exponents, they're just a way of indexing what we're talking about, since I want to save subscripts for different indices later on. Now let's say that the value we want this last activation to be for a given training example is y. For example, y might be 0 or 1. So the cost of this simple network for a single training example is AL minus y squared. The network for a single training example is AL minus y squared. We'll denote the cost of that one training example as C0. For example, y might be 0 or 1. So the cost of this simple network for a single training example is AL minus y squared. We'll denote the cost of that one training example as C0. As a reminder, this last activation is determined by a weight, which I'm going to call WL, times the previous neuron's activation, plus some bias, which I'll call BL. And then you pump that through some special nonlinear function like the sigmoid or a ReLU. It's actually going to make things easier for us if we give a special name to this weighted sum, like Z, with the same superscript as the relevant activations. So this is a lot of terms, and a way that you might conceptualize it is that the weight, the previous action, and the bias all together are used to compute Z, which in turn lets us compute A, which finally, along with a constant Y, lets us compute the cost. And of course, AL-1 is influenced by its own weight and bias and such, but we're not going to focus on that right now. Now all of these are just numbers, right? And it can be nice to think of each one as having its own little number line. Our first goal is to understand how sensitive the cost function is to small changes in our weight, WL. Or phrased differently, what is the derivative of C with respect to WL? When you see this del W term, think of it as meaning some tiny nudge to W, like a change by 0.01. And think of this del C term as meaning whatever the resulting nudge to the cost is. What we want is their ratio. Conceptually, this tiny nudge to WL causes some nudge to ZL, which in turn causes some nudge to AL, which directly influences the cost. So we break things up by first looking at the ratio of a tiny change to ZL to this tiny change W. That is, the derivative of ZL with respect to WL. Likewise, you then consider the ratio of the change to AL to the tiny change in ZL that caused it, as well as the ratio between the final nudge to C and this intermediate nudge to AL. This right here is the chain rule, where multiplying together these 3 ratios gives us the sensitivity of C to the change in ZL that caused it. You then consider some nudge to ZL, change what is the derivative of C, and it can be nice to think of each one as having its own little number line. Our first goal is to understand how sensitive the cost function is to small changes in our weight, WL. Or phrased differently, what is the derivative of C with respect to WL? When you see this del W term, our weight, WL. Or phrased differently, what is the derivative of C with respect to WL? When you see this del W term, think of it as meaning some tiny nudge to W, like a change by 0.01. And think of this del C term as meaning whatever the resulting nudge to the cost is. What we want is their ratio. Conceptually, this tiny nudge to WL causes some nudge to ZL, which in turn causes some nudge to AL, which directly influences the cost. So we break things up by first looking at the ratio of a tiny change to ZL to this tiny change W. That is, the derivative of ZL with respect to WL. Likewise, you then consider the ratio of the change to AL to the tiny change in ZL that caused it, as well as the ratio between the final nudge to C and this intermediate nudge to AL. This right here is the chain rule, where multiplying together these three ratios gives us the sensitivity of C to small changes in WL. So on screen right now, there's kind of a lot of symbols, and take a moment to just make sure it's clear. Clear what they all are, because now we're going to compute the relevant derivatives. The derivative of C with respect to AL works out to be 2 times AL minus Y. Notice, this means that its size is proportional to the difference between the network's output and the thing that we want it to be. So if that output was very different, even slight changes stand to have a big impact on the final cost function. The derivative of AL with respect to ZL is just the derivative of our sigmoid function, or whatever nonlinearity you choose to use. And the derivative of ZL with respect to WL, in this case, comes out just to be AL minus 1. Now I don't know about you, but I think it's easy to get stuck head down in the formulas without taking a moment to sit back and remind yourself of what they all actually mean? In the case of this last derivative, the amount that that small nudge to the weight influenced the last layer depends on how strong the previous neuron is. Remember, this is where that neurons that fire together wire together idea comes in. And all of this is the derivative with respect to WL only of the cost for a specific single training example. Since the full cost function involves averaging together all those costs across many different training examples, its derivative requires averaging this expression that we found over all training examples. And of course, that is just one component of the gradient vector, which itself is built up from the partial derivatives of the cost function with respect to all those weights and biases. From the partial changes stand to have a big conceptually nudged together our weight, WL. Or phrased differently, what is the derivative of C with respect to WL? When you see this del W term, think of it as meaning some tiny nudge to W, like a change by 0.01, and think of this del C term as meaning whatever the resulting nudge to the cost is. What we want is their ratio. Conceptually, this tiny nudge to WL causes some nudge to ZL, which in turn causes some nudge to AL, which directly influences the cost. So we break things up by first looking at the ratio of a tiny change to ZL to this tiny change W. That is, the derivative of ZL with respect to WL. Likewise, you then consider the ratio of the change to AL to the tiny change in ZL that caused it, as well as the ratio between the final nudge to C and this intermediate nudge to AL. This right here is the chain rule, where multiplying together these three ratios gives us the sensitivity of C to small changes in WL. So on screen right now, there's kind of a lot of symbols, and take a moment to just make sure it's clear what they all are. Because now we're going to compute the relevant derivatives. The derivative of C with respect to AL works out to be 2 times AL minus Y. Notice, this means that its size is proportional to the difference between the network's output and the thing that we want it to be. So if that output was very different, even slight changes stand to have a big impact on the final cost function. The derivative of AL with respect to ZL is just the derivative of our sigmoid function, or whatever nonlinearity you choose to use. And the derivative of ZL with respect to WL, in this case, comes out just to be AL minus 1. Now I don't know about you, but I think it's easy to get stuck head down in the formulas without taking a moment to sit back and remind yourself of what they all actually mean. In the case of this last derivative, the amount that that small nudge to the weight influenced the last layer depends on how strong the previous neuron is. Remember, this is where that neurons that fire together wire together idea comes in. And all of this is the derivative with respect to WL only of the cost for a specific single training example. Since the full cost function involves averaging together all those costs across many different training examples, its derivative requires averaging this expression that we found over all training examples. And of course, that is just one component of the gradient vector, which itself is built up from the partial derivatives of the cost function with respect to all those weights and biases. But even though that's just one of the many partial derivatives we need, it's more than 50% of the work. The sensitivity to the bias, for example, is almost identical. We just need to change out this del z del w term for a del z del b. And if you look at the relevant formula, that derivative comes out to be 1. Also, and this is where the idea of propagating backwards comes in, you can see how sensitive this cost function is to the activation of the previous layer. Namely, this initial derivative in the chain rule expression, the sensitivity of z to the previous activation, comes out to be the weight, WL. And again, even though we're not going to be able to directly influence that previous layer activation, it's helpful to keep track of, because now we can just keep iterating this same chain rule idea backwards to see how sensitive the cost function is to previous weights and previous biases. And you might think that this is an overly simple example, since all layers just have one neuron, and that things are going to get exponentially more complicated for a real network. But honestly, not that much changes when we give the layers multiple neurons. Really, it's just a few more indices to keep track of. Rather than the activation of a given layer simply being AL, it's also going to have a subscript indicating which neuron of that layer it is. Let's go ahead and use the letter K to index the layer L-1 and J to index the layer L. For the cost, again, we look at what the desired output is, but this time we add up the squares of the differences between these last layer activations and the desired output. That is, you take a sum over ALJ minus YJ squared. Since there's a lot more weights, each one has to have a couple more indices to keep track of where it is. So let's call the weight of the edge connecting this kth neuron to the jth neuron WLJK. Those indices might feel a little backwards at first, but it lines up with how you'd index the weight matrix that I talked about in the Part 1 video. Just as before, it's still nice to give a name to the relevant weighted sum, like Z, so that the activation of the last layer is just your special function, like the sigmoid, applied to Z. You can kind of see what I mean, right? Where all of these are essentially the same equations that we had before in the one neuron per layer case, it's just that it looks a little more complicated. And indeed, the chain rule derivative expression describing how sensitive the cost is to a specific weight looks essentially the same. I'll leave it to you to pause and think about each of those terms if you want. What does change here, though, is the derivative of the cost with respect to one of the activations in the layer L-1. In this case, the difference is that the neuron influences the cost function through multiple different paths. That is, on the one hand, it influences AL0, which plays a role in the cost function, but it also has an influence on AL1, which also plays a role in the cost function, and you have to add those up. On the one hand, it influences AL0, which plays a role in the cost function, but it also has an influence on AL1, which also plays a role in the cost function, and you have to add those up. And that, well, that's pretty much it. Once you know how sensitive the cost function is to the activations in this second to last layer, you can just repeat the process for all the weights and biases feeding into that layer. So pat yourself on the back. If all of this makes sense, you have now looked deep into the heart of backpropagation the workhorse behind how neural networks learn. These chain rule expressions give you the derivatives that determine each component in the gradient that helps minimize the cost of the network by repeatedly stepping downhill. If you sit back and think about all that, this is a lot of layers of complexity to wrap your mind around. So don't worry if it takes time for your mind to digest it all. Imagine you happen across a short movie script.
Before starting the next lecture, which is on LLMs, I would really like to share how satisfied I feel after starting this series of sitting here and streaming myself studying, because इसके पहले तो यार बिल्कुल ही कंसिस्टेंट नहीं था मैं, एंड मेरे दिन बस ऐसे निकल जाते थे, कुछ ना कुछ किया बस दिन निकालता था, यूज़ नहीं करता था, निकालता था, बस पास करता था टाइम को. बट इवन दो I'm somewhere around 25% efficient, कि मैं बाकी तो मैं जानता हूँ कि मैं टाइम पास भी कर रहा हूँ, बट एटलीस्ट 25% तक तो पहुँचा मैं. पहले तो मैं 25 पे भी नहीं था, पहले 5 पे भी नहीं था, टू बी ऑनेस्ट. एंड आई एम नॉट फीलिंग दैट गिल्टी राइट नाउ. और मैं भूल जाता हूँ, बार बार OBS चालू कर देता हूँ तो कि मल्टीपल इतने दिख रहे होंगे उसमें. बट या आई एम रियली फीलिंग गुड कि एक तो ML के लिए जो मैंने इतने समय से सोचा था कि मैं करूँगा, फाइनली मैंने स्टार्ट किया है अच्छे से पढ़ना. आई एम रियली थैंकफुल टू अर्पित कि उसने मेरे को इस चैनल के बारे में बताया. आई एम रियली हैप्पी कि आई एम लर्निंग द स्टफ दैट आई एक्चुअली envisioned to learn way back. एंड बस सोचता था, अब मैं कर रहा हूँ. एंड कैलकुलस से बहुत डर तो लगता है मेरे को अभी भी, बट एटलीस्ट मेरे को जैसे इंट्यूशन वाला पार्ट समझ में आ गया, तो कैलकुलस वाला भी मेरे को थोड़ा बहुत समझ में आ गया कि डेल W/del मतलब होता क्या है, कि what amount of changes in W are reflecting when we change in C, like del W/del C, यही मतलब है. एंड हाँ, आई थिंक all I needed was इंट्यूशन मिसिंग था मेरा मैथ्स में. बस फॉर्मूलेज को याद करके उसको सॉल्व करता था, rather than एक्चुअली रियलाइजिंग कि इसका इंटरप्रिटेशन क्या है. बट हाँ, लाइक अब मैं गाड़ी मुर्दे उखाड़ के कुछ मिलेगा तो है नहीं. बट हाँ, मैं समझ गया बैक प्रोपोगेशन के बारे में. अभी मेरा हाथ टूटा हुआ है, वरना फिर मैं इसको लिख के अच्छे से थोड़ा समझ लेता. इसके फॉर्मूलेज में मेरे को अच्छे से याद करने हैं. बट हाँ, लाइक आई एम गेटिंग द बेसिक गिस्ट ऑफ इट. एंड ऑल्सो गिस्ट होता है या जिस्ट होता है, मैं बार बार इसको यूज़ करता हूँ. वर्ड मीनिंग
gist,
Gist. The general meaning of something rather than all the. ठीक है हाँ gist.
gist,
So I'm actually starting to get
gist,
of it. But yeah, I'm really happy. Even though मैंने संडे गेमिंग करने में बर्बाद कर दिया, बट हाँ रात को मैंने थोड़ा बहुत कवर कर ही लिया, तो इतना गिल्ट नहीं हो रहा है मेरे को. मैं सोने जा पाऊँगा चैन से. बट या मेरा कितना पार्ट हो गया इसका. न्यूरल नेटवर्क्स में से 1 2 3 4 4 लेक्चर्स वर्थ मैंने कर लिया है, और बचे हैं 1 2 3 5 LLMs है. इसके बाद LLMs है, ट्रांसफॉर्मर्स है, हाउ डू AI images and videos actually work. These are interesting कि एक्चुअली कैसे रहा है ये. मैं मतलब वो तो मैजिक होता है, कोड आपने बस रन कर दिया, उसमें डेटा सेट को फीड कर दिया, बट वो हो कैसे रहा है. तो वो सब देख के मेरे को थोड़ा सा अच्छा लग रहा है कि ठीक है, ऐसा मैजिक नहीं है जो इसके पीछे मैथ से थोड़ा बहुत समझ में आ रहा है. या तो आई गेस आई एम गोना स्टार्ट दिस लेक्चर. एंड ट्रांसफॉर्मर्स मैं कल करूँगा, एंड गेट का प्रेप भी मैं कल से स्टार्ट करूँगा. बट ऑन अ पॉजिटिव नोट आई विल शो यू समथिंग. Even though nobody is watching these videos, and I don't think anybody is gonna watch these, but saying stuff feels like thinking aloud. I guess. भाई इंग्लिश बहुत ही ख़राब है. क्या कर सकता हूँ ये चीज़. ये देखो दोस्तों, ये तो इन दोनों को एक. इसमें म्यूज़िक क्यों आ रहा है? इसमें म्यूज़िक क्यों आ रहा है? अरे म्यूज़िक बजा देता क्या मैंने? पता नहीं म्यूज़िक क्यों आ रहा है. बट हाँ मैं फिर से भटक गया. मैं क्या कर रहा था कि 1 दिन पहले दिस टुडेज कंसिस्टेंसी. इवन दो वीकेंड्स थे बट स्टिल कंसिस्टेंसी. देख रहे हो दोस्तों, ये देखो कल रात भी गिरी थी मैंने स्ट्रीम. और कल से नया वीक चालू हो रहा है. आज संडे था, मंडे हो चुका है. कुछ नया थंबनेल ढूंढना पड़ेगा. ये सब बहुत बचकाना दिखता हुआ यार, बट मेरे को तो मज़ा आ रहा है सब करने में. अभी बेनिफिशियरी है और क्या चाहिए. बट हाँ, सो एक और वीडियो देखूँगा, एंड देन इसके बाद आई एम गोना रैप दिस लाइव. 3 घंटे की हो चुकी है, करीब 3.5 घंटे का हो जाएगा. उसके बाद फिर मैं एंड कर दूँगा. कल से और प्रोडक्टिव होना पड़ेगा भाई, ऐसे नहीं चलेगा. नौकरी चाहिए मुझे. चलो ठीक है, आई एम गोना म्यूट माय सेल्फ नाउ.
That describes a. Imagine you happen across a short movie script that describes a scene between a person and their AI assistant. The script has what the person asks the AI, but the AI's response has been torn off. Suppose you also have this powerful magical machine that can take any text and provide a sensible prediction of what word comes next. You could then finish the script by feeding in what you have to the machine, seeing what it would predict to start the AI's answer, and then repeating this over and over with a growing script completing the dialogue. When you interact with a chatbot, this is exactly what's happening. A large language model is a sophisticated mathematical function that predicts what word comes next for any piece of text. Instead of predicting one word with certainty, though, what it does is assign a probability to all possible next words. To build a chatbot, what you do is lay out some text that describes an interaction between a user and a hypothetical AI assistant, You add on whatever the user types in as the first part of that interaction, and then you have the model repeatedly predict the next word that such a hypothetical AI assistant would say in response, and that's what's presented to the user. In doing this, the output tends to look a lot more natural if you allow it to select less likely words along the way at random. So what this means is even though the model itself is deterministic, a given prompt typically gives a different answer each time it's run. Models learn how to make these predictions by processing an enormous amount of text, typically pulled from the internet. For a standard human to read the amount of text that was used to train GPT-3, for example, if they read nonstop 24/7, it would take over 2,600 years. Larger models since then train on much, much more. You can think of training a little bit like tuning the dials on a big machine. The way that a language model behaves is entirely determined by these many different continuous values, usually called parameters or weights. Changing those parameters will change the probabilities that the model gives for the next word on a given input. What puts the large in large language model is how they can have hundreds of billions of these parameters. No human ever deliberately sets those parameters. Instead, they begin at random, meaning the model just outputs gibberish, but they're repeatedly refined based on many example pieces of text. One of these training examples could be just a handful of words, or it could be thousands, but in either case, the way this works is to pass in all but the last word from that example into the model and compare the prediction that it makes with the true last word from the example. An algorithm called backpropagation is used to tweak all of the parameters in such a way that it makes the model a little more likely to choose the true last word and a little less likely to choose all the others. When you do this for many, many trillions of examples, not only does the model start to give more accurate predictions on the training data, but it also starts to make more reasonable predictions on text that it's never seen before. Given the huge number of parameters and the enormous amount of training data, the scale of computation involved in training a large language model is mind-boggling. To illustrate, imagine that you could perform 1 billion additions and multiplications every single second. How long do you think that it would take for you to do all of the operations involved in training the largest language models? Do you think it would take a year? Maybe something like 10,000 years? The answer is actually much more than that. It's well over 100 million years. This is only part of the story, though. This whole process is called pre-training. The goal of auto-completing a random passage of text from the internet is very different from the goal of being a good AI assistant. To address this whole process is called pre-training. The goal of auto-completing a random passage of text from the internet is very different from the goal of being a good AI assistant. To address this, chatbots undergo another type of training, just as important, called reinforcement learning with human feedback. Workers flag unhelpful or problematic predictions, and their corrections further change the model's parameters, making them more likely to give predictions that users prefer. Looking back at the pre-training, though, this staggering amount of computation is only made possible by using special computer chips that are optimized for running many, many operations in parallel, known as GPUs. However, not all language models can be easily parallelized. Prior to 2017, most language models would process text one word at a time. But then, a team of researchers at Google introduced a new model known as the transformer. Transformers don't read text from the start to the finish. They soak it all in at once, in parallel. The very first step inside a transformer is known as the transformer. Transformers don't read text from the start to the finish. They soak it all in at once, in parallel. The very first step inside a transformer, and most other language models for that matter, is to associate each word with a long list of numbers. The reason for this is that the training process only works with continuous values, so you have to somehow encode language using numbers, and each of these lists of numbers may somehow encode the meaning of the corresponding word. What makes transformers unique is their reliance on a special operation known as attention. This operation gives all of these lists of numbers a chance to talk to one another and refine the meanings that they encode based on the context around, all done in parallel. For example, the numbers encoding the word bank might be changed based on the context surrounding it to somehow encode the more specific notion of a riverbank. Transformers typically also include a second type of operation known as a feed-forward neural network, and this gives the model extra capacity to store more patterns about language learned during training. All of this data repeatedly flows through many different iterations of these two fundamental operations, and as it does so, the hope is that each list of numbers is enriched to encode whatever information might be needed to make an accurate prediction of what word follows in the passage. At the end, one final function is performed on the last vector in this sequence, which now has had a chance to be influenced by all the other context from the input text, as well as everything the model learned during training, to produce a prediction of the next word. Again, the model's prediction looks like a probability for every possible next word. Although researchers design the framework for how each of these steps work, it's important to understand that the specific behavior is an emergent phenomenon based on how those hundreds of billions of parameters are tuned during training. This makes it incredibly challenging to determine why the model makes the exact predictions that it does. What you can see is that when you use large language model predictions to autocomplete a prompt, the words that it generates are uncannily fluent, fascinating, and even useful. If you're a new viewer and you're curious about more details on how transformers and attention work, boy do I have some material for you. One option is to jump into a series I made about deep learning, where we visualize and motivate the details of attention and all the other steps in a transformer. But also, on my second channel, I just posted a talk that I gave a couple months ago about this topic for the company TNG in Munich. Sometimes I actually prefer the content that I make as a casual talk rather than a produced video, but I leave it up to you which one of these feels like the better follow-on.
ओके सो मैंने LLMs के बारे में भी पढ़ ही लिया एंड हाँ अभी मैं सही बोला तो मैं थक गया हूँ कि इसको फिर से मैं पूरा रिकैप करूँ बट LLMs आर बिग लार्ज लैंग्वेज मॉडल्स जिनमें आपको प्रिडिक्ट करा जाता है कि एक वर्ड के बाद क्या वर्ड आ सकता है एंड ये प्रिडिक्शन कुछ ऐसा रैंडम मैजिक नहीं होता है. इसमें भी वही होता है कि इसके अंदर बहुत सारे ट्यूनिंग रहती हैं, ठीक है. एंड आई गेस इसी को फाइन ट्यूनिंग LLM या फाइन ट्यूनिंग ट्रांसफॉर्मर कहा जाता है कि जो उसके अंदर के जो सारे नॉब्स हैं उनको ऐसे अच्छे तरीके से लाइक फाइन ट्यून करना कि जो आउटपुट आ रहा है वो हमारा ज़्यादा सेंस बना रहा हो एंड बेटर आउटपुट मिले हमको. जैसे कि जो प्रेडिक्टेड वर्ड है वो बेटर लाइक सेंस बना रहा हो एंड करेक्ट वर्ड हो इन अ वे. तो फाइन ट्यूनिंग आई गेस यही होता है. अब नाउ इट्स मेकिंग अ लॉट ऑफ सेंस बिकॉज मैंने उसका विजुअल देखा एंड मेरे को समझ में आया कि ट्यूनिंग मतलब होता भी क्या है. और हाँ इसमें भी बैक प्रोपोगेशन अटेंशन एंड फ्रंट समथिंग दो चीज़ थी, अटेंशन एंड फ्रंट समथिंग. तो ये दोनों प्रोसेस के बाद लगातार हाँ और उनको एम्बेड किया जाता है विद अ मैट्रिक्स. एक वर्ड का एक मैट्रिक्स रहेगा एंड उस मैट्रिक्स में चेंजेस करते रहेंगे एंड जिस वर्ड के लिए जो मैट्रिक्स है लाइक जो सबसे अच्छा वैल्यू देगा इन अ वे लाइक आई डोंट नो हाउ टू एक्सप्लेन इट बट जो बेटर रिजल्ट रहेगा जिस मैट्रिक्स का जैसे 9 क्लोजर टू 100% रहेगा ऐसा कुछ, तो देन वी विल चूज दैट. एंड हाँ ऐसे प्रिडिक्ट करता है. LLMs ये होते हैं प्रिडिक्ट करते हैं, ठीक है. और हाँ ट्रांसफॉर्मर्स भी यही है. मतलब ट्रांसफॉर्मर्स में बस ऐसा रहता है कि जो ओल्ड जो क्लासिकल वे ऑफ कंप्यूटिंग था वो था कि एक वर्ड को पहले हम पढ़ेंगे, उसके बाद नेक्स्ट वर्ड को पढ़ेंगे, उसके बाद नेक्स्ट वर्ड को पढ़ेंगे ऐसे कि उसके बारे में एनालिसिस करेंगे या पता नहीं, मैं समझ नहीं आ रहा कि बोलूँ कैसे मैं. बट ट्रांसफॉर्मर्स में क्या होने लग गया कि सारे एक साथ पैरेलली उनके बारे में हम उनको इंटरप्रेट करने लगे वर्ड्स को विच मेड इट अ लॉट ईजियर. एंड शायद से वीडियो में ये भी कहा था इफ आई एम नॉट रॉन्ग कि गूगल वाले लोगों ने ट्रांसफॉर्मर्स को स्टार्ट किया था. और हाँ ऐसा ही है. अभी मेरा थोड़ा दिमाग फट रहा है. आज मैंने जैसे ज़्यादा गेम खेल लिया, स्क्रीन टाइम ज़्यादा हो गया तो थोड़ा रेस्ट मांग रही है बॉडी. पर हाँ एक्चुअली मैंने एंडिंग में अच्छा क्लच मार लिया आज. नॉर्मली मैं इस समय ऐसे जयेश की स्ट्रीम देख रहा होता है या तो कुछ रैंडम वीडियोस देख रहा होता यूट्यूब पे. बट हाँ इट फील्स नाइस. एंड इसी के साथ मैं कल का स्ट्रीम के आज ही कर लेता हूँ, थोड़ा अच्छा लगेगा. इसी के साथ हमारा नया वीक चालू होता है. एंड गोल्स तो मैं कल देखूँगा आज भी. कहाँ है ये रहा. बात जरूरी है. ओके हाँ या सो दैट वाज इट फॉर टुडे स्ट्रीम. दोस्तों मुझे पता है कि आप देखते तो हो नहीं, बट अगर गलती से कोई आप देखेगा बाद में, मैं तो इन क्लिप्स को बाद में यूज़ करूँगा. जब मेरी नौकरी लगेगी ना तब मैं इन सब पे कॉम्पाइलेशन बनाऊँगा एंड शायद से एक यूट्यूब वीडियो बनाऊँगा कि हाउ आई डिड इट और समथिंग, आई डोंट नो. इसलिए मैं इनको ऐसा डिजिटल फुटप्रिंट रखता हूँ अपने पास. एंड हाँ यहाँ पर तो मैं हुई तो किसी को परेशान करने से अच्छा यहाँ पे आके खुद से ही बात कर लूँ. स्किज़ोफ्रेनिक भी नहीं लगाऊंगा क्योंकि आई एम स्ट्रीमिंग, यू नो. टेक्निकली आई एम टॉकिंग टू यू ऑल बट एक्चुअली देर इज़ नोबडी आउट देयर हु इज़ वॉचिंग दिस वीडियो. बट हाँ I do not get labeled as a schizo, so yeah that's what matters. That's all that matters. चलो ठीक है यार बहुत हो गया, मैं थोड़ा पागल सा हो रहा हूँ. 122 हो चुका है, 130 का टारगेट लिया था. लेट्स गो. दिस इज द फैमिली फ्रेंडली चैनल, ठीक है, यहाँ पे गाली वाली नहीं होती है. सो लेट्स गो, लेट्स रॉकिंग गो बोल रहा हूँ बाय द वे मैं. चलो यार फिर मैं यहाँ बंद करता हूँ स्ट्रीम आज की. नमस्कार. आर यू